The biggest threats in frozen landscapes aren't always hiding in the snow. Sometimes the real danger was inside the machine, or even worse, right on the outside. For decades, snow vehicles were built with such improvised, risky, and poorly planned solutions that looking back now, they feel like something out of a science fiction story. But at the time, they were seen as cutting-edge technology. Weak cabins, exposed engines, unstable steering, undersized parts — these were real characteristics that shaped the history of snow vehicles, putting workers in extremely dangerous situations on a daily basis. And the most shocking part? It was all considered normal until the failures started repeating themselves. Today, you're going to discover the most dangerous design features ever used in old snow vehicles, elements that eventually disappeared, and for good reason. Ready to find out how some of these machines turned into real death traps on tracks? Stick with me, because the last one on this list is so unbelievable, you'll wonder how it ever made it off the drawing board. Front ski steering. In the early decades of motorized snow vehicles, finding an efficient and low-cost way to steer these machines was a real challenge, and the most practical solution at the time was to mount skis at the front. Borrowed straight from dog sled designs, skis seemed like a simple way to control direction, while the rear tracks handled traction. It was a cost-effective and low-maintenance option. Adding another set of tracks up front would have meant a much heavier, more complex, and more expensive system. So, skis made sense, until the vehicles started getting bigger and heavier. Some of these machines weighed over 800 kilograms, and the skis, usually made from pressed steel or laminated wood, measuring around 1.2 meters long and 15 centimeters wide, just couldn't create enough friction or steering control in soft snow or crusty ice. With no power steering or advanced geometry, the entire steering system depended on the operator's strength. Turning the wheel was physically demanding, especially in tight spaces. And even when the steering was fully cranked, the vehicle often just kept going straight, sliding over the snow like it was on ice skates. That created incredibly dangerous situations, in curves, on downhill slopes, or in narrow trails. The driver had to anticipate each move by several seconds and hope the snow cooperated. On compacted snow, it was manageable. But in fresh powder, forget it. One Swedish model from the early 1950s even earned the nickname the drunk sled because, according to operators, it would drift from side to side even on a straight path. That machine is still on display today in a small museum in Sweden, with a little plaque carrying its infamous nickname. Now, let's be clear. Skis are still used today on modern snowmobiles, but that's where the similarities end. Today's models are lightweight, use tuned suspension, precision steering, and skis made of high-performance composite materials engineered for stability, even at high speed. In other words, the problem wasn't the ski itself. It was the crude, unbalanced, outdated way it was used in old machines. Technology evolved, and so did the ski. But if controlling direction back then was already difficult, the next feature made it nearly impossible for the machine to even stay on top of the snow. Tracks that were too narrow. In theory, any kind of track should perform better in snow than wheels. But in the earliest motorized snow vehicles, many designs used tracks that were simply too narrow, and that turned out to be a major mistake. Once again, the reasoning was both technical and economic. Wider tracks meant more material, more structural support, more weight, and required more engine power. Narrower tracks were lighter, cheaper to make, and easier to drive with underpowered engines. It looked good on paper, but not in the real world. Most of these models used tracks between 20 to 30 centimeters wide, built from metal segments or reinforced rubber belts with internal fabric layers. But they were far too narrow to properly distribute the vehicle's weight, which often exceeded 700 kilograms with cargo. What happened? The vehicle would sink, and fast.
On flat, packed snow, they could move, but get into soft snow or attempt a small incline and the tracks would just dig holes instead of pushing forward. It was common for drivers to stop, dig out around the tracks, place branches or planks underneath, and try to push themselves out manually. And with no front traction, once the rear tracks were stuck, the whole machine was going nowhere. Some models even came from the factory with shovels mounted on the cabin side, which says a lot about how often this happened. Narrow tracks also wore out much faster. All that weight concentrated on a smaller surface meant faster cracks, snapped joints, and belts slipping off. It was a temporary solution at best. Interestingly, some military vehicles from the 1940s used this kind of track for one reason only. They could be quickly swapped out in the field without disassembling the drive system. It made sense in battle zones, but for civilian use, it was a nightmare. Over time, wider and stronger tracks became the norm, at least 50 to 70 centimeters wide, with improved traction and materials. The performance difference was huge. Vehicles stopped sinking and started gliding over the snow like they should. But as the bottom of the vehicle improved, many models still had one big problem at the top, and that brings us to another classic engineering mistake.
Open cabin. Today, the idea of driving through sub-zero temperatures in a vehicle with no protection at all seems unthinkable. But for much of the last century, many snow vehicles were designed with completely open cabins. No doors, no windows, and sometimes not even a proper windshield. Why? Mostly to reduce weight and cost. Fully enclosed structures required more material, longer build time, and stronger engines to support the extra mass. For small utility vehicles, used on farms, by military patrols, or for power line maintenance in cold regions, skipping the enclosed cabin was a way to keep the project cheap and functional. In continuous use scenarios, open cabins also made it easier to get in and out quickly, load tools, or jump off when needed. But that practicality came at a high cost, in comfort and in safety. Now imagine driving for hours through strong wind in -20 to -40 degrees Celsius temperatures with no insulation at all. The cold wind cut across the face, snow hit directly into the eyes, and the engine's roar, completely uninsulated, vibrated through the chest. Gloves froze, goggles fogged up, and stopping even for a few minutes could lead to hypothermia. Many of these vehicles had only a basic tubular frame, maybe covered with canvas or sheet metal. Some had nothing at all. There were models so open that the operator sat with half their body exposed, relying only on whatever coat or layer they were wearing. And remember, this was long before modern thermal clothing. One curious example was a Canadian model used in the 1940s, which came with a military blanket tied to the driver's seat as an improvised heating system. According to reports, it was common for drivers to finish their routes with frozen eyelashes and purple fingers, if they even made it all the way. The shift to closed cabins only became possible when engines got stronger and body structures advanced, like lightweight steel and aluminum shells. Over time, thermal insulation, heated windshields, and cabin heaters became standard features. Enjoying this trip through machines that push the limits of logic and safety in frozen environments? Then hit that like, subscribe to the channel, and ring the bell, because around here we dive deep into stories time almost forgot. But even when manufacturers claim the cabins were sealed, some models still had one serious flaw, one that would sound like a joke if it hadn't actually been taken seriously for years.
Wooden cabin. The choice of materials in vehicle design has always reflected the technology and resources available at the time. And during times of scarcity, especially during and after the World Wars, wood became a practical and accessible solution for snow vehicle cabins. It was easy to cut, lightweight, reasonably cold resistant, and most of all, cheap. Many early snow machines used full cabin structures made from plywood panels, about 10 to 20 millimeters thick, used for the walls, roof, and even the floor. Some were covered in protective paint, canvas soaked in resin, or thin steel sheets. But the base was always the same: wood. The problem? Wood offered minimal protection in an accident. In collisions, the cabin could split apart easily. In rollovers, the roof would collapse. And in the worst cases, splinters from the inside could cause serious injuries to anyone on board. To make matters worse, wood absorbs moisture, making it prone to rot, warping, and even internal freezing. It was common to see parts of the cabin swelling, cracking, or peeling apart after just a few winters. Many operators had to rub the joints with used oil or grease just to keep things from falling apart. And in case of fire, the risk increased tenfold. With the engine often installed right in front of or even inside the cabin, a single fuel leak or electrical spark could turn the whole vehicle into firewood on tracks. There's a documented case of a model used in 1950s Finland that caught fire after the exhaust system broke loose and overheated the internal wall. The dry wood, combined with poor ventilation, made the fire spread so fast that the driver barely escaped through the side window. The vehicle was completely destroyed in minutes. These models were meant as temporary solutions, and in many ways they did help bring motorized transport to remote areas. But as time went on, wood gave way to stronger, lighter metal structures, and with that, one danger was eliminated. But while the upper body of the vehicle was already a concern, what sat beneath it left even less room for error.
Steel tracks that couldn't take the pressure. On paper, using steel for snow vehicle tracks seemed like a no-brainer. Strong, durable, and resistant to extreme conditions. But in the earliest snow machines, engineers didn't anticipate that not all steel can handle the constant pounding of frozen terrain, buried rocks, and the endless stress of irregular surfaces. Most early tracks were made of stamped steel segments, connected by metal pins and rollers, sometimes bronze. Some of these segments were made from sheets thinner than 5 millimeters. Fine for lab tests, but in real-world use, they cracked easily. Why so fragile? 2 reasons: keeping the vehicle lightweight and cutting manufacturing costs. Advanced alloys weren't widely available, so instead of treated or high-grade steel, they used plain carbon steel, which corroded quickly and lost strength over time. It was common for tracks to develop cracks at welded joints or for an entire segment to snap when hitting a hidden rock or ice ridge. And when it broke, it wasn't just inconvenient, it was dangerous. A broken link could jam the track, damage the drive system, or even cause the vehicle to veer off course suddenly. Operators often had to stop mid-route, pull off the damaged track by hand using heavy tools, and try to fix it right there in the freezing cold. That's why many crews carried portable kerosene-powered welders, ready to patch things up in the field. There are reports from 1950s Russian expeditions where maintenance teams spent more time repairing the tracks than actually moving. The constant freezing and thawing cycles made the metal brittle fast. But the danger wasn't just mechanical, it was survival. If the vehicle broke down in a remote area with no backup or communication, the operator could be stranded for days with limited supplies and life-threatening cold. Eventually, these fragile steel tracks were phased out, replaced with wider, reinforced models made with steel, rubber compounds,
and better rollers that could handle ice and corrosion. But as dangerous as external breakdowns were, some of the most serious threats started inside the cabin itself.
Oversized engines inside the cabin. Today, it's hard to imagine a snow vehicle with an engine inside the cabin, right next to the driver. But for years, that was the only way to keep things compact and practical. Many old snow vehicles, especially military and industrial ones, were designed with the engine mounted directly behind or beside the seat. The reasoning was technical. Keeping the engine inside protected it from the cold, made repairs easier in freezing conditions, and allowed for a shorter overall design, essential for narrow trails and remote work. But the downsides were serious. These engines were usually large 4 or 6-cylinder blocks, up to 5 liters of displacement, gasoline-powered and mounted on simple metal brackets with no acoustic or heat insulation. The result? Constant vibration, deafening noise, and scorching heat. In some cases, 1960s Russian models, crews carried buckets of clean snow inside the cabin, melting them to cool both the engine and the people inside. It was a rough workaround, but it became part of the job. Eventually, engines were moved into dedicated compartments, insulated with thermal blankets, and ventilated properly. Comfort, safety, and reliability improved overnight. If you think these wild solutions were as dangerous as they were creative, just wait until you see what's next. Hit like, subscribe, and ring the bell because we've got even more unbelievable stories on the way. Coming up next, when the engine wasn't just inside the cabin, it was basically in the driver's lap.
Engine practically in the driver's lap. If having the engine inside the cabin was already a problem, some older snow vehicles took it even further, placing the engine so close to the operator that they were practically sharing the same seat. In certain compact models used for farming or patrol work, the engine block was mounted between the driver's legs or directly beneath the seat, with no cover, no separation, and no insulation. Why? It was all about space optimization. These vehicles needed to be short, maneuverable, and cheap to build. Integrating the engine into the seat base reduced parts, simplified construction, and kept the overall footprint small. But it also turned the cabin into a walking safety hazard. Most of these engines were 4-cylinder units, air or water-cooled, producing between 25 to 40 horsepower. And they got hot, very hot. With no barrier, the heat would rise straight into the operator's legs, warming the seat, the floor, and everything around. And often, there wasn't even a proper lid on the engine bay. Burn injuries were a real possibility. Some experienced operators would cover the engine with wet rags or blankets on longer routes, just to bring the heat down a little. That is, assuming there weren't any fuel or oil leaks, which in such tight quarters created the perfect recipe for an onboard fire. One Canadian model from the 1950s even had a notorious quirk. The driver had to keep a wrench between their knees, not for convenience, but because the engine vibrated so much the mounting bolts would loosen mid-drive. In other words, the driver could feel the engine coming apart while sitting on it. Thankfully, this layout didn't last long. It was soon replaced by safer designs with dedicated engine compartments and proper ventilation. But for a time, it wasn't unusual to see a snow machine operator with a melting seat and shaking knees. And as hard as that is to believe, the next feature wasn't just dangerous for the driver, it was a threat to anyone nearby.
Exposed airplane propeller on the rear. Yes, this actually happened. In the early days of snow vehicle experimentation, some engineers tried adapting airplane propellers to push vehicles across snow and ice. The logic was simple. If tracks couldn't gain traction, maybe raw propeller thrust could move the machine forward. And it worked, at least in a straight line. But adding this kind of propulsion to a ground vehicle created a massive safety hazard, especially for anyone standing behind it. These propellers were usually mounted at the rear, driven by a high RPM gasoline engine, often producing 50 to 100 horsepower. Many had over 1.5 meters in diameter, spinning at dangerous speeds, completely exposed, with no grille, no cage, no shielding. Just an open spinning blade capable of inflicting fatal injuries in an instant. This design was mostly used in experimental or prototype vehicles operating in extremely remote regions like Siberia, Alaska, and northern Canada, where terrain made traditional traction impossible for much of the year. Rear visibility in these machines was almost non-existent. No mirrors, no sensors, and with the engine roaring, operators couldn't hear if anyone was approaching. That made the propeller a silent and constant threat, especially during boarding, maneuvering, or sudden stops. In 1947, a film crew documenting one of these test vehicles in Canada had to stop shooting after one of their tripods was sucked into the propeller and launched over 20 meters. No one was hurt, but the incident was enough to underline just how dangerous the system was. Some later models tried using protective metal cages around the propellers, but those reduced thrust efficiency and caused turbulence. The result? Many continued using fully exposed blades until the end of their production, and until this kind of solution was finally phased out for good. Today, a vehicle like this would never pass even the most basic safety standard. But back then, risk came bundled with innovation.
These were the most dangerous features ever used in old-school snow vehicles. At the time, they were seen as clever solutions, but over the years, they proved to be disasters waiting to happen in environments where one mistake could mean disaster. Weak cabins, exposed engines, unstable steering, fragile frames. These machines belonged to an era of trial and error, where engineering still had a long way to go, and where the operator often paid the price. They weren't just vehicles. They were symbols of a time when courage, creativity, and improvisation went hand in hand with every expedition. And despite all the risks, they laid the groundwork for the safe, reliable machines we have today. Now, tell me in the comments, which of these features did you find the most shocking? Which one did you never expect to exist? And if you had to drive one of these, which would you dare to try? And of course, if you love content like this, make sure to hit that like button, subscribe to the channel, and ring the bell, because every week we dive deep into the wildest machines, the most bizarre mistakes, and the incredible history of snow tech and engineering. See you in the next one.